Today we're going to talk about volume of prisms and cylinders. Volume is measured in cubic units. It quite literally is the number of cubes of that size that you can put into an object. Congruent objects have equal volumes. That's what VO1 says. So if you have U, a length, and G1 is a measurable figure, and G2 we're going to let be a figure in space. If G1 is congruent to G2 in space, meaning there's an isometry that will map one to the other, then I know that G2 must also be a measurable figure and their volumes are equal. We can talk about the ordered union boundary property in space, just like in the plane. And all this says is an object may be divided into sections that do not overlap. And by doing so, we're going to be able to find volumes by breaking up our solids into pieces. So VO2 says the volume of the whole is equal to the sum of the pieces. So we're going to use the ordered union boundary property with this property that just says in order to find the union of solids, I just add up their volumes. The first shape that I'm going to talk about is a prism. A prism is a polyhedron or a solid formed with faces that are all polygons, and it has congruent faces that are in parallel planes. Those faces that are congruent in the parallel planes we call bases, and the faces around the outside are called lateral faces. Where two lateral faces meet, we call a lateral edge. Where a lateral face meets a base, we call a base edge. So let's see what EMF says about it. A prism is a polyhedron solid formed by extruding a polygonal region of a plane via a translation parallel to a line that does not lie in the same plane. So in other words, we have two bases. I have a translation that takes this base to the top base or a parallel plane. We can have right versus oblique prisms. And a right prism, these lateral edges meet the lateral base at a right angle. If it's oblique, that's not the case. So in my right prism, I have this triangular base. The other one is right over the top of it. But in this one, you can see that I have this base and my top base has been pushed over. Now we call the distance between our bases the height, and the slant height is when it's oblique. It's the distance from one vertex of a base to the other vertex. We can find the volume of a prism by multiplying the area of a base times the height of the prism. And the height of the prism is the distance between the bases. So let's see what our EMF book says. Let U be a length, let G be a solid box-shaped figure, three of whose adjacent sides have U lengths P, Q, and R for some P, Q, and R. Then G is a measurable figure, and the volume is P times Q times R. So if I'm looking at a rectangular base, it really is the length times the width times the depth, or the height, or however you want to say it. The dimensions multiplied together. Now, the thing I like about this formula is if you find the area of the base and multiply by the height, it doesn't matter what shape the base is. But again, if you have this rectangular prism, you can indeed multiply the dimensions. I'd like you to work on exercise 42. Press pause on your video, and when you're ready for the answer, press play again. Now, I did this as one solid figure. You could have divided it up into rectangular prisms here and here. There's a number of ways to do it. You should get the same answer regardless. But I decided to make this front stair step section be a base because I knew I had one in the back as well. So I found the area of this base here and I multiplied by the distance between my bases. So I ended up finding the area of that base was 123 square units. Then I multiplied by the height of the prism and I found out that it was 1,230 cubic centimeters. The next solid figure that I'd like to talk about is a circular cylinder. A circular cylinder is similar to a prism, except my base is not a polygon. My base is a circle. And these bases are in parallel planes. We can have a right circular cylinder, in which case this lateral edge is perpendicular to the base, or I can have an oblique circular cylinder where I have one base that's been pushed over. The distance between the bases is called the height, and if I'm dealing with an oblique cylinder, the slant height is measured from one point on my base to the other point on my base edge, such that it's perpendicular to the base here. The volume of a cylinder can be calculated the same way the volume of a prism can be calculated. It's the area of the base times the height. Now, the base in this case is a circle, so the formula would be pi r squared times h. And indeed, that is what we're told. So we're going to let u be the length, let u cubed be volume of a prism or cylinder. It's the product, usually labeled h, the u height, and the area of its bases. Well, that's nice. Now we're extending this definition to a prism and also a cylinder. And I like to categorize my formulas that way. It helps me remember what they are. I'd like you to try exercise 43 now. Press pause on your video, and when you're ready for the answer, press play again. So in this problem, we have a right circular cylindrical soda can where the volume is 21.656. The height of my soda can is 4.83 inches, and I would like to find the diameter in inches. So I start off with my formula, which is area of the base times the height. I know my volume is 21.656. That's equal to pi r squared times the height, 4.83, which was given. I divide both sides by 4.83 pi, and then I used their decimal approximation for pi, and I found r squared was equal to 1.427, and I took the square root, and I found that my radius was 1.2, and when I multiply by 2, I get my diameter, 2.4. Volume under magnification. Now, if you remember when we magnified in the plane, it took our area and we multiplied by the scale factor squared to get the image's area. When we're dealing with volume in space, we can find the new volume by taking your scale factor cubed and multiplying by the old volume. The next object I'd like to consider are pyramids. Pyramids have a polygon as the base, and then triangular lateral faces around the outside. So the height goes from what we call the apex, where my lateral faces meet, down to the base. It's the perpendicular distance. The base can be any polygon. We typically name our pyramid based upon the name of the base. So in this case, it's a regular pyramid. And this one is a right triangular pyramid. My triangle down on the base is a right triangle. Now, this is a right pyramid where my vertex is directly over the center of my base. This is an oblique pyramid. Now, the next thing I'd like to talk about is finding the centroid of a quadrilateral. So we know how to find the centroid of a triangle, And remember, the centroid is the point where all the medians intersect. So if I start with this quadrilateral region and I divide it into two triangles, I can find the centroid in each. So in the left-hand triangle, I draw my segment from P to the midpoint of the side, and for this triangle, also from R to the midpoint of the opposite side. Then I can find the centroid, because I know the centroid is 2/3 of the distance to the point M, away from the vertex. So the distance between P and my centroid is 2 times the distance as from my centroid to the midpoint of the opposite side. So I have my centroid here of this triangle, my centroid here of that triangle. Now I connect the centroids and I find the point on it that balances things out. So the area of this triangle is larger than is this triangle. So this point is going to be closer to the larger side. So in our book, it says the centroid G of quadrilateral PQRS is the point that divides XY in the inverse ratio of the areas of triangle PQS and RQS. So I would take the area of triangle RQS and divide by the area of triangle QPS. And then I would take that ratio and apply it to my segment. So it's going to be closer to this side if this is larger. So I would take this ratio and apply it here. So for example, if I found that the ratio of the area of triangle RQS to triangle QPS was 3/2, that would mean that I would need my centroid to be closer to Y than is X. So this segment here would be divided like so. So rather than 3 being on this side, it's on that side. So I would find this point based on this distance and divide it into a 3:2 ratio. So I want you to consider a centroid of a planar figure. It's always going to lie on a line of reflective symmetry. So if a planar region has a line of reflective symmetry, doesn't always, then the region's centroid must lie on that line. This is because the line of symmetry divides the region into two congruent halves, which therefore have the same area. Each half has its own centroid, and because of the symmetry, those centroids are symmetrically placed relative to the line of symmetry. The centroid of the whole region is then the point of the segment determined by the two half-region centroids that divides the segment in the ratio 1:1. That is, it is the midpoint of that segment, but the line of symmetry is the perpendicular bisector of that segment. Consequently, the centroid is a point of the line of symmetry. So now let me just draw something here. Let me draw a kite. Wait a minute, it's not perfect. But let's just see here a minute. Now I have this line of reflective symmetry going through my kite. And if I drew in my centroids here, this divides like that. My centroid would be here and here, and it would be equally spaced. It would be equally spaced on either side. So now when I just draw this segment in, because this is the same distance away from here as is this, my centroid of the whole quadrilateral will lie on this line of reflective symmetry. There is a 1:1 ratio because the area of this side is the same as the area of that side. So if I do have a figure that has a line of reflective symmetry, that centroid will be on the line. I'd like you to work on exercise 47. It's asking how far from V the centroid is of each of these regions. Press pause on your video, and when you're ready for the answer again, press play. So I first found my centroid of the rectangular region. And to do so, you could divide that rectangle up into two triangles. Join this vertex with its midpoint, the opposite side, same thing here. And then my centroid would be placed 2/3 of the distance away from my vertex to here. So same thing on the other side, and what you'll find is that then the centroid of the quadrilateral, when I draw this, has to land right here. That's because this triangle is congruent to that triangle. So I'm going to erase this a minute so we can see it just a little bit better. So now I know that this centroid is going to be where my diagonals intersect right here. And if this is 4 long, that means that this distance is 2 away. Now, how far is this centroid from V? Well, it's going to be 12 plus 2, so 14 away. Now, the next question is, how far is V from the centroid of my triangular region? Well, the centroid is going to be along this segment here that joins my vertex to the midpoint of the opposite side, and it's going to be 2 times the distance from V as it is from the midpoint. So since this is 12, I can find how far that is from V by knowing that this is 2 times x, make that x, so I have 3x equals 12, x then is 4. So now I know that from the midpoint to D is 4 away, and from D to V is 8 away. So how far is V from the centroid of my triangular region? It's 8 centimeters away. Now I know where those are, and I'd like to find the centroid of the pentagonal region. Now let me erase here. So in order to figure that out, what I need to do is know first that the centroid of the pentagonal region is going to be somewhere along the segment that joins this centroid of my rectangle to this centroid of my triangle. Now I have to figure out the area of my triangle and the area of my rectangle. Well, the area of my rectangle is base times height, so that's 24. The area of my triangle is 1/2 the base times the height. 1/2, 6, times the height of my triangle, 12, is 36. So the centroid, or the balancing point of my figure, is going to be closer to the triangle than it is to the rectangle. So the area of my rectangle is, as a ratio to the area of my triangle, is 2 to 3. So looking at this, I know that from F to D, I want to be 2 times x. And from E to F, I want to be 3 times x. So I add these up, 5x, and I know the distance between here and here is 6. And I let that be equal to 6. I divide both sides by 5, and I find that's 1.2. So now I know that DF is 1.2 times 2, or 2.4, and I know that VF is now 8 plus the 2.4. So 10.4 would be my answer. Your classwork and homework today are exercises 44 through 46 and also exercise 48, as well as a volume worksheet that I've posted online. Have a great day.